All right, good morning, everybody. I'm going to introduce you horizontal projectile motion. This is when you fire something or launch something horizontally through the air such that it moves forward and falls at the same time. The physics of this is nothing that we haven't learned already. It's still kinematics, but I want to develop the concepts because two things are happening at once. They're independent of each other, but they combine to give us an overall trajectory that I'm going to map out here in this little cannonball situation. And then we'll solve some problems. I want us to understand that there's no new equations here. It all comes from our kinematics. You just got to be able to set it up correctly. Where you're gonna, the twist is there's going to be vertical information and horizontal information, and you must distinguish between the two. So let's get right into it. So we're going to fire a cannonball off a certain height, 125 meters, and we're going to fire it at 10 meters per second forward. Okay, so we're going to assume air resistance is negligible, and we're going to try to figure out what the trajectory looks like, right? So here's the cannonball at time equals 0, and it's at an initial height of 125. So you know it's going to fall and move forward. You probably have an idea of what the trajectory is going to look like. We'll show you how we'll develop it. So the key concepts to doing the equations is right here. This is the most important statement of all projectile motion. When we get to more complicated firing at an angle, nothing has changed. First statement is the horizontal motion is constant. We're moving at a constant speed. And essentially the reason for that is there's nothing to oppose it. We're again ignoring air resistance. Gravity is trying to pull it down, but gravity only affects it vertically. It does not affect it horizontally. And the vertical motion is no different than free fall. As soon as this leaves the cannonball or the cannon barrel, it is in free fall. So the vertical motion is accelerated. Okay, and so you just have to treat each one independently. So I have over here a table of where it is horizontally and where it is vertically after 1 second of time. So let's develop the values independently. So let's take the horizontal. How would we calculate the horizontal motion as a function of time? Well, if we have constant, that means acceleration is 0. So that means our x is simply going to be equal to v naught t. The 1/2 at squared is 0, so I'm going to ignore that. So that's pretty straightforward. So after 1 second, if I fill in this table, at time 0, it's at 0. After 1 second, it's going to go 10 meters, then 20 meters, then 30 meters, 40, and then 50. Okay, so I'm just doing v times c for that. So I'm just going to plot this right now as if there was no gravity. So it's going to be here after 1 second, that's 10 meters, 20 meters, 30 meters, 40 meters, and then if I put a fifth one out here, roughly 50 meters. Okay, so notice we have evenly spaced dots indicating constant motion. Now let's look at what happens when we turn gravity on. So the ball isn't going to go along the horizon line here. It's going to start falling, and it's going to start falling in an accelerated manner. So if we want to calculate where it is height-wise, we have to use equation for height. And then because it's accelerated, we're going to want to use y equals y naught. So there's an initial height, so I don't want to ignore that there, plus v naught, and I'm going to put a y now, okay, in the vertical direction. So we have to distinguish between horizontal and vertical. And what I should have done over here is I should have put a vx there to indicate the horizontal speed, whereas in this equation it's the vertical speed times time plus the vertical acceleration, which is g. I'm going to put a t squared there. So this might not be obvious, but let's be clear. The initial vertical velocity is 0. It's not launched up or down, so this term becomes 0. And g is negative since it's down, so I'm going to turn that plus sign into a minus sign. Okay, so my height at any given time is equal to my initial height minus what happens due to falling, and that's 1/2 gt squared. So I'm just going to write below here, I'm going to rearrange it. That's going to be y equals y naught minus g, we're going to call 10 for argument's sake. So half of 10 is 5, and so 5 times time squared. So let's fill in this table here. So at time 0, our height is 0. After 1 second, so if I go to here, 1 squared is 1, times 5 is 5, our initial height is 125, so 125 minus 5 is 120. So I'm going to now plot this in. So I've gone over 10, I'm going to drop down to 120. So that's where the ball is after 1 second. Again, it's moved forward 10, it's fallen a distance of 5, which gives us a height of 120. After 2 seconds, 2 squared is 4, 4 times 5 is 20, 125 minus 20 is 85. So we are going to be at position 85. So here is 80, 85. I'm going to go over, and I'm going to go under where it's moved over, so it's right about there, approximately. After 3 seconds, 3 squared is 9. 9 times 5 is 45. 125 minus 45 is 80. I think I made a mistake on 2. I don't know what I was thinking. So it's 125 minus, sorry about that. 125 minus 20 is 105. Okay, I just had a brain fart there. So let's try that again. So 105, it's going to be right here. And then we're going to be at position 80 after the 3rd second. Okay, so sorry about that. All right, after 4 seconds, 4 squared is 16. 5 times 16 is 80. 125 minus 80, I believe, is 45. Okay, so 45 is right there. Go under there. And then 5 seconds, 5 squared, 25 times 5 is 125. 125 minus 25 is 0. In other words, we've hit the ground right around there. So 0, let me just fill that in properly. See if I can get this right. Apologize for that. Okay, so the point being is if I connect these dots, I don't get a diagonal. I should get a nice parabola. So the hallmark of any trajectory when you launch something forward and up or horizontal or down is you're going to get parabolic motion. And that's actually is a general thing. Whenever you have a motion where one direction is constant and the other direction is accelerated, you will get a parabola. If it was moving at constant speed vertically and horizontally, then it would be a diagonal. And if it was accelerating in both directions, it would turn out to be a diagonal as well. All right, so let's turn now to problem solving. When you go to solve a problem, like if I say I launch something with a certain speed, how much time is it in the air, or how far does it go, we want to do our VTAX equations. So we just have to set up horizontal and vertical and understand what the information that goes in there using the key that horizontal is constant, vertical is accelerated. Okay, so we're going to make 2 columns, and I've got it right here. X is horizontal, Y is vertical. The only information that goes in both columns is time. So understand, in that trajectory I showed above, the time that it takes the cannonball to go forward, 1, 2, 3, 4, 5 seconds, is the same time that it takes to fall these different spots. So the time to fall the full height is the same time to move forward to that position. Okay, so let's do a problem and I'll set it up. I say I'm firing an arrow, so I'm firing an arrow level to the ground, and it leaves a bow at a speed of 45 meters per second, and initially height was 1.5 meters. Okay, again, let's make clear the angle, theta, is 0, so we're not firing it up, nor are we firing it down. We want to know how much time is it in the air, and how far away does the arrow land from the archer. Okay, it's going to hit the ground. We're going to assume there's no obstacles along the way. Then we can ask some speed questions. So the approach is, all right, first thing, what are we looking for? We're looking for time. So if I go to my table, or if I go to my table, I have a time, so I could figure out the time maybe by looking at the horizontal motion, or maybe I have to figure it out by the vertical motion. So we don't know that quite yet. So let's look at the information we have. So it leaves a speed of 45 meters per second. So that's clearly initial speed. Now you have to ask yourself, is that a horizontal speed or a vertical speed? Well, since we're firing it level to the ground, that's horizontal. So that's 45. What about the vertical speed? Just like the problem above, it's not aimed up or down, so vertically and initially is not moving. So that's always a piece of information for horizontal motion. Its initial vertical speed is 0. Okay, we're given a height of 1.5. So height, that's a distance. Is it a vertical or horizontal? Yeah, right, that's a vertical distance, so that goes over in this column. Our horizontal, we don't know. In fact, that's what we're trying to find out in part B. So what that leaves us really is the acceleration. And that's where the concept above. What's going on horizontally? Well, we said it's constant motion. So that means its acceleration is 0. What's going on vertically? It's accelerating at free fall. So that's going to be negative 9.8. Alrighty. So now we can start solving. We don't really have any information about final speed. We'll worry about that later. It doesn't really come into play in this one. So I want to find time in the air. Well, I got 2 places I can find time, either horizontal or vertical. Which one has 3 pieces of information? Well, the horizontal has this and this, but we're missing two other pieces. So we can't use horizontal, so we have to use vertical. So we have three pieces of information. So what equation would help me tie together distance, time, acceleration? Well, the one we use quite a bit. So I'm going to do it in terms of y. I'm going to say my change in height equals vyt, right? I could actually put vy naught. I can put two subscripts there, plus 1/2 gt squared. Actually, I would put minus 1/2 gt. All right, let me step back a second. I would say plus 1/2 at squared. We're understanding a is negative 9.8. So if this term is 0, because our initial vertical is 0, please don't put 45 in there, because that's horizontal, and we can't mix horizontal and vertical. Then if I solve for time, I see it's 2 times the change in height divided by g. I'm going to substitute in g for a, and the square root of all that. Okay, I'm sure you can do that algebraically. So you're going to see that a lot. 2 times 1.5 is our change in height. Actually, the change in height is negative because we're going from 1.5 to 0 divided by negative 9.8. Therefore, we can take a square root of a positive. So if we do that properly, crap, I don't know what it is. I think it's about 0.5 something seconds. I'll let you figure that out, okay? Because the numbers aren't essential here. Now I can, so I've got, okay, so I went ahead and actually calculated it. So 0.55 seconds. It's going to be in the air. And note that that speed, or that time, is independent of the speed, okay? All right, so how far away will it land? Well, that's looking for this. Now that I know that this is 0.55 seconds, I can go ahead and use the horizontal information, and I can just say x equals x naught plus vx naught t. I'm not going to put in the acceleration part because there is 0 acceleration. A mistake would be to put 1/2 gt squared there. So x naught is 0, so this is simply the launch speed, or the speed times 0.55 seconds, and then that will give us an answer of roughly 25. Not quite. Okay, what's the horizontal speed just before it hits the ground? So that's final speed. You could do a calculation, but if you look back at the information, what do you know about horizontal? It's constant. So if horizontal is constant, that arrow is still going to be going 45 forward as it goes to the ground. So imagine this is the trajectory of the arrow. When it's fired from the bow, and here is the ground, it's got to follow that path. It's still going to be moving this way 45. How about vertical speed? In other words, what's this? Well, we have enough information. We can say the vertical speed, Vy, equals the initial vertical speed plus gt, right? Because acceleration times time. And so that's simply going to be, that's 0, 9.8 times 0.55. Okay, so for argument's sake, let's just say that's 5.5. All right, I'm going to treat g as 10. So at the moment just before it hits the ground, it's moving this way, 5.5. So I could then ask, what's the overall speed? And I want you to recognize that as vector sum of two perpendicular quantities. So it's going to be moving this way, where that value, I'm just going to put as a v. V is equal to the square root of 5.5 squared plus 45 squared. And then I could ask you, what's the angle? And you could say the tan of the angle that makes, right? So there's this vector, and there's an angle there. Well, let's see, make sure I get this right. Yeah, so the tangent of that is going to be 5.5 divided by 45. So we're not going to focus on this so much, but that is fair game. So to finish up the tutorial, I want you to do the following two example problems. Okay, the answers are at the bottom. I've kind of set up the initial information for as carries over from the previous problem, so that's why it's called D, E, and F. And the idea is now the archer, right, if here is the bow, right, firing the arrow, okay, we're going to try to hit a target that's over here somewhere. So the question is, will the arrow make it to the target? And if it does, will it go over the target, or will it fall in just enough time to hit the target? So it's a combination of where are we horizontally versus where are we vertically, and it's a little bit more involved, but it's still the same kinematics. And then the last problem is a classic where you're in a moving object in the air and you drop something, in this case a bomb. Okay, so the bomb just doesn't fall straight down, it moves forward with the helicopter and fall, so it's going to get a take a parabolic trajectory. So the question is, how far in advance do we have to drop it in order